Okay, good day. The topic we will discuss today is the Gust effect. So, first, what is this Gust effect? No? Or in short term, what is this Gust? No, GUST. So let's differentiate between the gust and the sustained wind speed. So gust wind speed is the instantaneous wind speed. So if it means it's instantaneous wind speed, it means that it's just there for a second and it will not be sustained. That's why it's different from the sustained wind speed. So it's given for a short period of time. It's a short-lived burst, no? As you can see here, it's a short-lived burst. So therefore, it is big. Its speed is larger compared to the sustained wind. No, so what is this sustained wind speed? So sustained wind speed is average speed over a period of time. Sometimes it is 1 to 10 minutes. So gust and sustained wind speeds are sometimes attributed to typhoons, like for example Typhoon Yolanda, and so much more. So this is the difference between gust and sustained wind speed. So, as you can see, the sustained wind speed can be found in NSCP 2015 in some of its figures, while gust wind speed is attributed to what we call gust effect factor. So later we will discuss what is effect factor, and we will have some examples on how to compute the gust effect factor, especially for flexible buildings. Okay. So as you can see here, this is the Typhoon Yolanda. So this is a real data from Typhoon Yolanda from NASA, no? From NASA. So as you can see, the sustained wind speed of Typhoon Yolanda is 155 miles per hour, or that is equivalent to 250 kph. But the gust, as you can see the gust here, no? As you can see the gust is 190 miles per hour, much more bigger and much more powerful compared to sustained wind speed. So in computation of our wind load, we account for this gust, or in Tagalog, it's what we call pagbugso. Pagbugso means sudden wind. Uh, so therefore, it's really needed to account for this gust. But this gust, the effect of gust is mostly attributed to the response of the structure, meaning the dynamic response of the structure. So later, as you can see, gust effect is much more prevalent or much more important in structures that are flexible. So as you can see, it is defined in NSCP 2015 that flexible structures have a fundamental frequency, or fundamental period. No, let's say fundamental frequency. So they called it N1. That is less than 1.0. So if your frequency is less than 1.0, it means that your structure is flexible. So later we will discuss that and how should we get the frequency of the structure. So let's go to uh, what we call the gust effect factor. So this gust effect factor I will show you later, in which what provisions it is in NSCP 2015 and also in ASCE 7-16. So the gas effect factor is part of the designed wind speed, or the design wind load, or the design wind pressure. So it's a part, no? So the gas effect factor is this. Okay, that is the gas effect factor. So the gas effect here for the internal pressure, it is computed as a whole along with CPI. So this is not the gas effect factor we are talking about, but as you can see, this is group, no? So we will have other lectures about this, especially in the enclosure classification of buildings, like for example, enclosed, partially enclosed, partially open, and open structures. But we will now focus on this letter G, this gas effect factor. So according to Holmes, the gas effect factor, or the gas is an amplification factor, no? It is called an amplification factor. So it amplifies, as you can see, it amplifies uh, the design pressure. So this design pressure or design wind pressure is what we are gonna use in the design of our structure. So it is important to consider the gas effect factor because this is an amplification factor. So according to Holmes, the gas effect factor or what we call the gas loading factor, as you can see here, it's loading. Ah. So it is the ratio of expected maximum response of the structure to the mean response. So that is the Gust effect factor. So the response here, what we call the dynamic response of the structure. So meaning it is associated with frequency or period of the structure. So let's see. What am I talking about? Let's go to this. First, I will show you this provision here. So you can see the provision in NSCP 2015 that the gas effect is in section 207A.9.4 or sorry, this 207A.9.1, the gas effect factor. So as you can see, for rigid buildings, it is permitted as 0.85. So what do you mean by rigid buildings? So rigid buildings are those the fundamental frequency is greater than 1 or greater or equal to 1 hertz. So that this is a rigid building, no? This is what we call a rigid building. So the opposite of a rigid building is what we call the flexible. So flexible or dynamically sensitive buildings are those fundamental frequency is less than 1 hertz. You can say that oh, I'm sorry. It is ano, I am yes, right. Uh, let's go to the meaning. So you can see here. Yes. As you can see, we can go to this definition, no? So you may read the definition of flexible buildings or building that is uh, okay. So building or other structure as rigid. So rigid buildings are those with greater than or equal to 1 hertz. Like I said, you consider the building as rigid if it has a fundamental frequency of greater than 1 hertz. While a structure that is flexible building. Okay, here. So, building or other structure that is flexible. As you can see here, flexible. This is from the standards of American Society of Civil Engineers 7-16 code. It means that the fundamental frequency is less than 1 hertz. No? So, that is right. No? So, fundamental frequency here is N sub 1 that is less than 1 hertz. Okay. So this is flexible. So this is flexible. So less than 1 hertz. So in rigid, so the fundamental frequency here is greater than or equal to 1 hertz. So later I will show you how should we get the fundamental frequency of a structure, no? So how should we get that? So let's go back to the Gust effect. So as you can see, the Gust effect has two formulas, but if it is rigid, that means that the fundamental frequency is greater than 1. Use 0.85. So don't bother to calculate this, but also you can also calculate because this is easy. But as you can see, just get it as 0.85. But it is very important to compute this one if it is flexible. So first determine your structure if it is flexible by means of any rational analysis, no? Any rational analysis like they said here. There is approximate natural frequency, but if computation or any computer aided design or modeling is available, use the fundamental frequency there. But you can compute it as what we call approximate natural frequency using these formulas. But anyway, I will show you, no? So these are the formulas. So I will give you an example here later, and we will try to check our calculation if it's right by using this example calculation in chapter commentary 26 of the ASCE. ASCE. So also NSCP also has I don't know where's that part, the sample calculation, but we can use the sample calculation of ASCE. So first, let's go to the computation. So I have here some computation. So you can see, as you can see here, the very first thing that you need to compute is the VC. So I did not put also, this is V bar over V bar sub Z bar. So this one. So as you can see, let's try to compute. Okay. So this is the sample calculation. Okay, sorry. Okay, let's try to input some. Uh, let's try to input some. By the way, I will show you how to get the okay. So I'll show you to get. So first, just analyze it using the what you call that set load cases to run. Just the modal analysis. Because the concern here is not any loading, but the concern here is to get the fundamental frequency. So just run the modal analysis so that you will get the modal properties of the structure. So this structure is a 28 meters span, or the opening here is 28 meter by 36 meters. What you call this one? Uh, Gable frame truss. Okay, so let's try to analyze the modal analysis first so that we can get the um, fundamental frequency. So you can see after you analyze it, there will be this tab, analysis result, then get the modal information here, modal periods and frequencies, and show it in the table. As you can see, the fundamental frequency here is 0.579, meaning this is so it's equals to 0.58 or 0.579. So as you can see here. So as you can see, this is 0.579. It means this is flexible. So since this is flexible, we should try to compute the gas effect factor. So don't just assume that it's 0.85. Compute it. Because this is what we call a fundamental frequency. No? This is given. No? So let's try to compute it. Later, I will try to compute it now. But first, let us, so I will not use this one. So later, we will use I will use it. So first, let's try to compute this one now. Okay, okay. Dito na lang. Later, I don't have any H. So I just show you where should we get the participation factor, no? The modal participation factors. Sorry. The periods and frequencies. I just show it to you because I don't have any. I don't know H. I don't know the V. So let's try to assume. Okay. So we have the, I think the roof mean height is in this one is 14 meters. And let's assume that the sustained wind speed from the map is 300 kph, because there is a website later that I will show you in future videos that we can get the sustained or the wind speed V in kph. So we have this one. So this one, we can get this in table 26.11-1 or 207. So what table am I, does it mean? So this one is, as you can see here, this is the table. So for different exposure, so just look for my other videos about my explanation about exposure categories. So these are the parameters that we need. These are what we call the terrain exposure constants. And use the SI units here. Use these SI units. Yes, this. So we assume that is exposure category B in an urban area. So we will construct this warehouse in an urban area. So that's the thing we need to use here. As you can see. Um, okay. So yes, this one 28 by 36. So we assume that it is normal to the ridge. So therefore, the B is perpendicular to the wind direction, that is 28, and L is 36. So, okay, I think I'm wrong. I think it's 36 here. Sorry. It is 36 and this is 28. So, okay, later just try to I have other videos for explanation about that B and L. So 0.579, let's copy that, then put it here, 0.579. So as you can see, our NA, eta H, I don't know what's the meaning of this, I forgot. So let's try. This is what we call the vertical decay parameter. So our vertical decay parameter for this type of structure is 1.017, etc. So this is, I think, so I use MATCAD. So this is automatic computation. Then therefore our gas effect factor is 0.22, 1.22. So this is amplification of about 22%. So do not use 0.85 because it is not rigid. As you can see in the computation of ETABS, it is flexible, no? Frequency is 0.579. That is the meaning of flexible building in based on ASCE, no? So as you can see here again, the meaning of flexible is fundamental frequency less than 1 hertz. So less than, okay? As you can see, flexible, that is less than 1 hertz. So anyway, this is a flexible building, so therefore we need to use, no? We need to use the formula as defined by ASCE 26.11 and also in NSCP 20 point, what you call that, 20.207A.9.1. So let's try to see if both the definition is the same with the ASCE. Okay, where's the definition here? So okay, the definition is, there's no okay. Okay, the definition for flexible buildings is fundamental frequency less than 1 hertz. So the same. So anything that your fundamental frequency, or what we call the very first frequency, or the frequency of the first mode of your structure, that is mode 1, that is what we call, or the lowest frequency is what we call the fundamental frequency. And if it is less than 1 hertz, then use the formula. So it's very important to use this amplification factor. As you can see, that it amplified the design pressure. It amplified the design pressure for almost 22%. So it's very important, class, that you compute. So let's try to check our computation if it's right. We will use the example computation given in the commentary section of ASCE. So let's try to check if it's the same, so that I can also assure that my computation is, or my, what I have put here in MATCAD is right. So for exposure B, these are the parameters. You can see this is a alpha bar. Sorry, I can't put bar in top. This is B bar. This is Z min and etc. So as you can see, the H here is given as, we don't bother with rigid. We don't bother with rigid. We bother with what we call flexible building, and that is okay. 183 meters again. I don't know why this is so big. Then our basic wind speed. So this equivalent to 115 mph to kph. So that is 185 kilometers per hour because I'm using SI units. 185, 183, and our kph is 185. Then it's automatic that our basic, why is it that it's okay? So this is 51. So this is 51 meters per second, and our, what we call the mean wind speed at effective height is 42.1 meters per second. That is 42.099. So it's right. Then our reduced natural frequency here, as you can, is 2.982. Okay. Sorry. I did not change other I did not change other parameters, so that is 30 30. So our parameters is 30 30. So with normal to the wind, with normal to the wind. Right. Then depth parallel to the wind. So assuming that this is I don't know, to the ridge or to the parallel. So anyway, make sure to create your own MatCAD class or create your own Excel. Later, I will show you Excel because it is one of your assignments to create an Excel for this so that uh, you don't bother to calculate it step by step, but you have a prepared spreadsheet. No? So let's try to check our reduced natural frequency. Our reduced natural frequency is let's try to to check what are okay, sorry. So we didn't change the natural frequency. Our fundamental frequency is zero point 0.2 hertz. That is zero point 0.2. So I did not bother to change. So that 0.579 is from the ETABS. So zero point 0.2. Then let's try to check. So that's right. Our reduced natural frequency now is 1.03. So don't worry, I will give you a paper about this example calculation so you can create your own calculation. So our resonance response factor Rn is 0.129, so it's exact 0.129. So our N1 is also exact 1.029, 1.03. Then our what you call this one parameters. So our vertical decay parameter is 4. It's 4, right? Crosswind decay parameter is 0.656, just a bit not exactly exact, but 0.667, 0.656. And along wind decay parameter is 2.223. And this one is 2.195. So our resonant factor for H, B, and L are as follows: 0.219, that is exact; 0.676, 0.671, it's very near; 0.350 or 0.349 is also near; 0.353. Then our what we call this one, L. Where's the L? So so it's given 97.54. Our what you call this power law exponent 1/3. This can be seen from table 26.11-1. Then our turbulence length 216 meters. So it's right. So this is 216.795. Then we go to the resonance factor. As you can see, the term resonant. So it's very important that wind gives us a resonance. If you can see the video, search for the video, the Tacoma Bridge. The Tacoma Bridge has a resonant frequency that is the same with the wind, and that is why there is a resonance. So there is a resonant frequency there. It is very important because wind is a dynamic load. And when the natural frequency of the wind matches the frequency or natural frequency of the structure, it creates resonance. And that is why the Tacoma Bridge has collapsed. You can watch that video in YouTube. Just search for the Tacoma Bridge collapse. Then our GR, the resonant peak factor is given as 3.4, 3.4. This is fixed, guys. C 26.11.5 for ASCE, and for NSCP section 207A.9.5. Our resonant frequency GR is exact 3.787. Then our IZ and Q, that is the turbulence intensity, is 0.201. That is okay, that is right. Then our Q, so there's no Q here, it's only Q squared. So if you square this 0.785, that is let's try Q squared. Okay, right. Q squared is 0.616. It's correct. Our Q is the same with this given here. Then finally, computing the gas effect factor 1.173, we have 1.176. So it's very important, class, that as you can see here, this my computation is what you call that, verified by the example calculation from the ASCE, no? It is a sample computation by ASCE. As you can see, As the natural frequency decreases, the gas effect factor increases, and that is very important. Do not assume 0.85 always in a rigid structure. So like for this one, in our wind loading, I did not define wind loading yet here. As you can see, the load patterns in the wind. So we don't assume 0.85. So we put the 1.17 if that's the computation. That's why it's very important to compute the Gust effect. Okay, class. We can check here. I also have my. This is your assignment. This is your assignment. So as you can see here, just change those 0.57974 earlier that term. So anyway, this is your part, no? As you can see, if I change the exposure category from C, the gas effect factor increases. And from D, it also increases. So, yes. So, the greatest exposure that could give us the highest gas effect factor is letter D, while the smallest one is letter B. So I have an explanation about that because exposure category D is the exposure in which there is no obstruction. It is an open space where the wind can freely blow your building, and that is why it's very important, no? Because wind along with earthquake is a very catastrophic event that could destroy your structure, and that is why loading, the correct loading and correct determination of load is very important in structural design, in this case in your steel design. So do not really assume that you have a rigid building unless you try to compute the fundamental frequency of it, and that's why we have some uh, good softwares that could determine the modal properties, especially the fundamental frequency. So I think that is it, our topic, gas effect. So it is accounted for in our design as a factor. Okay, thank you. And